In section 12.2, we're going to carry on the idea that we saw in section 12.1, which is that when we had things in 2 dimensions for vectors, we can carry on the same ideas in 3 dimensions, and we're just going to have another number in the bracket. So in 2 dimensions, we had this thing I, which is the vector 1, 0, and j, which is 0, 1. And I was a unit vector in the x direction, j was a unit vector in the y direction. So to have a unit vector in the x direction in 3 dimensions, it would look like this, 1, 0, 0. Okay, so 1 unit in the x direction and no units in the y or z directions. J is going to be the same thing, a 1 in the y direction and 0s everywhere else, okay? And this is the y component, so we get a 1 there, 0s everywhere else. Now obviously we're going to need a third thing though, because we've got a z-axis as well now. So we'll call this one k, and that's going to be 0, 0, 1. That's going 1 unit in the z direction and no units everywhere else, okay? So in the same way again as before, if we have a column vector PQR, then that is P times I plus Q times J plus R times K. So this vector here is the same as this vector here, because this many lots of this vector plus this many lots of this vector plus this many lots of this vector makes this vector here. So we're just using this, what we used to call IJ notation is now IJK notation. So if you have well, just to make sure we've covered everything, if this is the position, if this is a point, the position vector at that point is 1, 5, minus 2, and in IJK notation it's I plus 5j minus 2k, all right? And if we look at example 5, we can do things like this. If I get a vector called A, which is 2, minus 3, 5, and I get a vector called B, which is 4, minus 2, 0, then 4 lots of vector A would be 8, minus 12, 20. 4 lots of 2, 4 lots of minus 3, 4 lots of 5. So 4A would be that. 4A plus B would be 8, minus 12, 20, plus 4, minus 2, 0. And when I add vectors, as I did in 2 dimensions, I just add component-wise. I add the first components, I add the second components, and I add the third component. All right? So we can add vectors the same way as we did before. We can multiply vectors by scalars the same way as we did before. We just got an extra thing thrown in. A couple of other examples that they do for this section. And the first one is, we've already said how to find the magnitude of a vector. Well, do we remember that if we have a vector A, then we can say that A hat means the vector A, but a unit vector in the direction of vector A. So I'm going to divide by modulus of vector A. And if you can't remember that result, go back and have a look in the chapter for the last year's, the year 12 vectors chapter, and we have that result. Well, we can do that thing again then. So if we have a vector 2, minus 1, 4, we can do that vector divided by its modulus, and the way we divide it by its modulus is 1 over 2 squared plus minus 1 squared plus 4 squared, all square rooted. So that's dividing by the modulus is timesing by 1 over the modulus. 2 minus 1, 4. So if I work out what this number is and times by it, then we're sorted. So that number there turns out to be a 21. So 1/21th, sorry, 1 square root of 20, 1 over square root of 21 times by this. So 2 over root 21 minus 1 over root 21, 4 over root 21. That vector there is a unit vector in the same direction as A. And the last thing that, and this is a brand new one actually, if you have a vector, and I'm going to try and draw this, perhaps you'll be better off looking at the diagram on page 340 in the textbook, because it just looks a little bit neater there. But there's vector A, just any sort of random vector on an XYZ axis. Now, if we've got a vector A, I can draw in this triangle here, which is a right angle. So I drop a line from the end of vector A straight to the x-axis. Because it's going straight to the line, there's a 90-degree angle between them. And I might be interested in this, which is the angle between vector A and the x-axis. And if I'm interested in that angle, then this line here, this distance here, is the x-coordinate of vector A, isn't it? So cos of that angle, and in the book they're calling that angle theta subscript x to show that it's the angle between the vector and the x-axis. So cos of that angle is this distance here, which is the x-coordinate of vector A, divided by this distance here, and that distance there is the magnitude of vector A, isn't it? Okay, so cos theta is x over A, where x is the x-coordinate of vector A, and mod A is the magnitude of vector A. Now we can come up with, and obviously then the same thing works, the angle between the vector and the y-axis, theta y is y over mod of A, and same for z. Now we can come up with lots of sort of little facts like that. There's all sorts of things you can do with three-dimensional vectors, but that one is one that the exam will particularly want us to know, so we need to specifically revise it. And I think really that is it. In example 7 they ask us to just apply this formula. In example 8 they're asking to show that a triangle is isosceles, and again we're just applying the new bits. I mean, we've seen this so many times now. Now they've given us a new bit of knowledge, we have to fold it into all the other maths that we know. So what do we know about isosceles triangles? We know they've got two angles the same, so we need to work out that that this triangle that they show us has got two angles the same size. We could do it by showing that it's got two lengths the same size. When we look at it, what can we find out? Can we find out the lengths? Can we find out the angles? In this particular example, it looks to me like we are finding the lengths, not the angles, aren't we? So we find out the distance from A to B, the distance from O to A, the distance from O to B, and those three things, two of them are the same and one of them is different. So we know that two of the sides are the same length, one of the sides is a different length, so we know it's an isosceles triangle. That's exactly what we would have done in 2 dimensions. This time there's an extra number in the brackets, and we can't draw a diagram very easily, so we're just going to have to go through those motions without the diagram. But that is all the advice really I can give you on section 12.2. I know there are going to be all sorts of other things in the exercise, but the whole point of this chapter really is to get you thinking of vectors and set you puzzles that are not algorithmic questions where you follow the same method every time, but where you just use your knowledge of vectors and your knowledge of geometry and your other knowledge of maths to solve the puzzle that you set. So I can't give you I can't really give you any more useful examples. I can just show you how the new techniques work, and hopefully your mathematical perspicacity will do the rest for you. So good luck with section 12.2.